Imagine designing a custom deck of cards using the 26 letters of the English alphabet. Let's say each card must have exactly 6 letters. The central constraint is that every pair of cards must share exactly one letter. In the language of mathematics, each card is a 6-letter subset. The intersection between any two of those subsets must always have a size of exactly 1, no more, no less. Adding a third or fourth card sounds easy enough, but try to randomly assign letters and a system instantly falls apart. You will inevitably pick a letter that creates a second match with a previous card, or you'll miss making a connection entirely. Guessing your way out of this is impossible. The rules create a hidden structural trap that rapidly depletes your available options. To understand why, we have to pause this 26-letter game and shrink our universe of letters down to a microscopic scale. Let's start small. We have exactly 4 available symbols, A, B, C, and D, and we are only allowed 2 symbols per card. This diagram shows the 3 possible cards we can build, AB, AC, and BC. They perfectly satisfy our one shared symbol rule. Notice how this forms a geometric shape. Every edge of this triangle represents a card, and every pair of edges meets at one endpoint. You might spot that the 4th symbol, D, goes completely unused. If we try to squeeze in a 4th card using D, it still has to connect to all 3 of the existing cards. But a 2-symbol card only has 2 slots. It physically cannot make 3 distinct connections without breaking our rule. Let's scale up slightly. We now have 5 available symbols, and each card holds 3. Building the first 2 cards is simple, ABC and ADE. They share exactly 1 letter, A. Now try to build a 3rd card. It must connect to both of these previous cards. But it cannot reuse the letter A, because then all 3 cards would share A, creating too many overlapping connections in the total system. Here is the bottleneck. The first 2 cards completely exhausted all 5 available letters. A new card must pull a letter from card 1 and a letter from card 2, but doing so instantly forces a double match somewhere. Our local choices are trapped by a rigid global limit. If we add just a single letter to our pool, giving us 6 total symbols while keeping 3 symbols per card, the system suddenly breathes. Adding that 6th letter makes this balanced 4-card set possible. If you trace the intersections across this grid, you'll see that every single pair of cards meets exactly once, no missing connections and no double matches. This reveals the underlying mathematical law governing our deck. There is a constant tension between the physical space on a card and the total pool of symbol pairs available to draw from. This is a foundational principle of combinatorial design. Any specific pair of symbols, like A and B, can exist together on at most 1 card. If they appear together on 2 different cards, those 2 cards would share at least 2 symbols, violating our core rule. Because pair reuse is strictly forbidden, the absolute maximum number of cards you can create is dictated by how fast your deck burns through every available pair in the alphabet. Armed with this knowledge of pair depletion, we can finally solve our original challenge, 26 letters with 6 letters per card. This equation calculates our upper bound by checking how many non-repeating pairs exist. For a 26-letter alphabet and 6-letter cards, the math establishes a hard ceiling. It proves that no more than 13 cards can ever be created. But there is a big difference between a mathematical bound proving 14 cards is impossible and the structural reality of actually building 13 valid cards. This chart shows the ultimate solution. It is a mathematical architecture known as a Steiner triple system, organizing our 26 letters into exactly 13 cards. Every letter is used exactly 3 times, generating exactly 78 unique single-symbol intersections. What starts as a seemingly simple tabletop card game rule quickly demands an incredibly precise, rigid structure to survive. It forces us to bridge basic counting with the deep geometric beauty of combinatorial design.